Our next talk is from Nicolas Bellouin, who's going to be talking about reports and background notes of EASA's Aviation Non-CO2 Effect Network, otherwise known as ANSEN.
Thank you very much, Nellie, and hello everybody. So I'm Nicolas Bellouin of the University of Reading and the IPSL in Paris for the Clean Aviation project at the moment. And yes, and I would like just to kind of draw your attention to some work that has been done in the Aviation Non-CO2 Expert Network of the European Aviation Safety Agency. And so I'm going to go a little bit through the deliverables of that project so far. So just to give a bit of context, you may have seen or read the report here shown on the right by EASA on non-CO2 impact on climate. That was quite an influential report in the sense that it kind of brought non-CO2 from aviation to the attention of policymakers. And for that reason, especially in Europe, non-CO2 emissions are quite high on the political agenda. And there's been multiple initiatives launched on non-CO2 since that report, a few initiatives before, but a strong increase since 2020. And that means that the landscape became a bit fragmented with a lot of projects doing their things. And so the European Commission, they wanted to have some kind of project, a meta project that looks at all that science, all those results, and try to make sense of all this. And this is what ANSEN is. So ANSEN technically is a research project, but that feeds on other projects. And there is a strong interest and involvement by the different Directorate General of the European Commission in ANSEN. So ANSEN acts as a technical forum because there's clearly a need for consensus, for discussion around the aviation non-CO2 question. So the idea is to build this coordinated approach and provide objective, timely, and credible technical advice to the aviation ecosystem at large and also to policymakers. So ANSEN is made of experts from Europe, from various stakeholder groups. You see a picture of the members at the kickoff meeting here on the slide. And so people come from different organizations, either policy making, academia, scientific research in general, industry, and civil society, including NGOs. And the idea is to together develop a common understanding to inform discussions and decision making in various areas around non-CO2. So how it's done? So ANSEN is organized as several tasks, and that I will just review quickly the tasks that have been achieved and those that are ongoing. So here on this list, the first two tasks were essentially kind of trying to draw on methods by the Intergovernmental Panel on Climate Change on how to do a scientific assessment, how to work with uncertainty, and how to communicate the level of uncertainty. Task 3 was to learn a little bit about other aviation environmental impacts, so noise and air quality impacts, and how policymaking around those impacts can inform policymaking around non-CO2. Task 4 is looking at uncertainties and looking at research gaps and prioritizing them. This was led by David Lee and Ulrike Burkhardt, and the report on that task will be published later this month. Task 5 is about sharing best practice and, for example, linking the work that is done at ICAO, CAEP level on emission aviation modeling with non-CO2 models, and I will talk a little bit more about that in a moment. Task 6 is keeping lists of all the projects and initiatives around non-CO2, and we'll see that there are quite a few. Task 7 is on communication, so it's communication to workshop like this one, but also for the creation of what we called background notes, so essentially kind of distilled scientific information for policymakers, so documents of about 4 to 5 pages on a very focused subject, and I coordinated that activity, so I will talk about the free background notes that are already on the website and the upcoming notes. Then we have a few perhaps more technical tasks which are ongoing. So I'm not going to talk about that, but that's essentially looking at different ways to address non-CO2 climate effects of aviation. Then other tasks that are ongoing. The task 11 should be interesting. The idea is to apply the IPCC uncertainty framework on aviation non-CO2 questions. 2 questions have been selected. The one is benefits from the use of SAF. So what can we say with confidence on that subject? And the second is on contrail avoidance navigation. Essentially, try to assess the likelihoods that contrail avoidance could reduce contrail relative forcing. And also in that task is essentially to see, to try to put together these different projects that have tried to mitigate or looked at mitigation measures for non-CO2 and see how we can compare their findings. Then tasks 12 and 13 look at more towards policymakers and also funders of research to see how to address the gaps that have been identified and how to best inform policy making, especially in Europe. So let's have a look at some of those reports. So first, the report on that looks at that counts the projects on non-CO2. So the report is online on the ANSEM website, so you can check whether your favorite project is included, and if not, tell us. So far we've counted 64 programs / projects / initiatives on aviation non-CO2 since 2010, but the vast majority of those have started after 2020, the 49, and they cover a broad range of topics from climate science to aircraft emissions, operations, carbon markets, economy, and fuel. And a lot of those projects are funded at European level in the different funding programs or by the joint undertakings, Clean Aviation and EASA. But also and increasingly at national government level in France, in the UK, and in Germany especially, and by research councils. The Task 5 report, so here this is to try to make the link with ICAO CAP emission modeling. So in CAP, they run emission models based on a couple of aircraft performance models, and this is historically linked to air quality, to NOx and particular matter emissions. And those techniques have improved in time, and further improvements are still needed. And to feed into that, we need ground tests of engine emissions, but also and increasingly important for non-CO2 flight chase experiments to have emissions at cruise level. At the moment, the emissions of NOx and non-volatile particulate matter, so soot, are extrapolated from certification data in the landing and takeoff cycle based on correlation model, based on hypothesis on fuel flow and thrust. And those correlation models require continuous improvement. At the moment, the estimate performance on those emissions at cruise level are about 3% for CO2, 15% for NOx, and 20% for NVPM soot. Importantly, and perhaps increasingly importantly, if we move to low soot fuel or engines, the knowledge base for volatile particulate matter emissions is much less developed, and so needs work and measurements. So moving to the background notes, so there are 3 background notes have been published so far. The first one is on the timescales of the climate effects of aviation CO2 and non-CO2 emissions. So the notes are a lot on the question of CO2 equivalence metrics, but here I wanted just to put in everybody's mind the importance of this. Of those different time scales. The figure shows what happens if you take the best estimates of variety forcing by Lee et al. 2021 into a climate model, a simplified climate model, and you look at the impact on surface temperature of the different components of the aviation non-CO2 and CO2 impacts. And you see that, for example, if you look at Contrail, which is this AIC dark green line, you see that contrails and NOx dominate the short-term response, while CO2 in red is initially a smaller contributor. And in the case of the numbers from Lee et al., the crossover point is about around 10 to 15 years. Where CO2 starts to dominate the climate impact of aviation, and then the total impact eventually is the same as CO2. So first, that tells us that non-CO2 impacts, have kind of decadal scale effects, so they're not negligible. But ultimately, this is of course CO2 that will need addressing. So, of course, that was just 1 year of emission, but the aviation emits in a continuous way. So what happens if you now consider several years of emissions? So here on the left is what happened to CO2 and non-CO2, so in red CO2 and non-CO2 in blue. If you increase emissions by 1% per year, for example, and you see that the non-CO2 will keep on increasing, but at, in general, a lower rate than CO2, because CO2 accumulates in the atmosphere. If you look now on the right, this is a case where you emit at sustained level. So, for example, you manage to limit CO2 emission by using a fraction of SAF. And you see that if you emit a sustained level over many years, well, CO2 in red will keep on accumulating, will keep on increasing. But the non-CO2, you see, will reach a maximum after about a decade. And after that, that will not increase because the warming from past non-CO2 emissions has essentially vanished. So this is this behavior that kind of drives the kind of mantra of how to reduce the climate effect of aviation, and that you need to reduce the CO2 emissions because you need to stop this accumulation. You need to stop the red line from increasing, while not increasing, but preferably also reducing the non-CO2 emissions. Of course, you can do it. You can also address non-CO2 first before addressing CO2. The second background note looks at the climate effect of aviation contrail, and it opens with the physics of how contrails impact climate, and Olivier mentions that a little bit. But I want to come back on two statements in those notes. The first one is looking at the statement, a large fraction of total contrariety forcing is caused by a minority of flights. This is a statement that is very important for contrail avoidance because that tells us essentially you don't need to reroute every single flight. And it's true, scientifically speaking. It's just a consequence of the shape of the distribution of contrariety forcing. But interestingly, it comes in two ways, depending on the study you look at. In the first view, which is the flight-by-flight view, for example, running COSIP on flight and then looking at the distribution and say, well, this is the 2% of flights that contribute to X% of total contrariety forcing. And then there is a second view, which comes from climate modeling. So climate modeling is more thinking in terms of flight density distributions and weather patterns. And here you see that the same information is expressed differently. Here it says, for example, 70% of contrariety forcing is exerted by contrail outbreaks happening on 25% of days. So essentially there are a few days where there are many contrails, and this is where we get most of the forcing. And you see that those views, even though they say kind of the same thing, it's not exactly clear whether they are reconciled at the moment and whether they are actually talking about the same flights. And this is a problem that needs studying. This is often when you talk to pilot or air traffic controller about avoidance, and they feel there is something strange of, we are told that the forcing is due to this superposition of contrail for many flights, but then I'm told to look at flight-by-flight things. So here, this is really the reconciliations that we need to work on and to study better. The second statement is it remains difficult to predict which flights belong to the minority that exerts the strongest climate effect, and this is what Olivier just said as well. So there are different sources of uncertainty. There's forecasting, limitation in our understanding of contrariety forcing, especially contrail persistence, and the tools used to quantify that forcing, and the question of interactions between contrails. So what happens if you reroute a flight but you don't reroute the next flight, or what happens if you form a contrail into an existing cirrus. And all those uncertainties exist, they won't disappear, and Olivier showed that, well, it's okay, we can work them into our tools to get some kind of measure of risk of avoidance. There is one uncertainty at the moment that resists being put into a kind of uncertainty frameworks at the moment. And this is what the statement at the bottom of the slide refers to, is that at the moment we don't yet know whether the flights that exert the strongest radiative forcing are also those that are most effective at warming surface temperature. So that's a question of adjustments, that's a question of efficacy of the forcing. There is reasons to believe that will depend on the weather situation, and especially how fast you can recover humidity that has been consumed by contrail formation. But that's clearly one of, well, personally, I think is the most important uncertainty at the moment because it kind of threatens the whole idea of contrail avoidance. This uncertainty is unfortunately only accessible to climate models. So this is really the work that we do in the climate community is to work strongly towards better understanding those aspects. Finally, the third background note is on the benefits of changes in fuel composition on CO2 emission. And so it says first that yes, you can affect these non-CO2 emissions by changing the fuel composition, which is good but not too surprising. Also, it can be noted that in the case of non-volatile particles, soot, changing the engine technology can also deliver large reductions and sometimes much larger reductions. And before going on, it needs to be noted that the scientific evidence we have for the moment is limited to a small number of sustainable aviation fuel types, essentially SAF, and essentially because that's what has been used by ground gauge and flight tests, but there are increasing number of tests using different fuel, including hydrotreated kerosene. So if we look at the different non-CO2 emissions, what can we say from the benefits of change in fuel composition? Well, for NOx and carbon monoxide, there's minimal impact from fuel. It's completely driven by the engine technology. Water vapor, there's been measured about 10% increase in water vapor emissions from fuel with higher hydrogen content, including SAF. For soot, which is a big question for Contrail, there's clear idea that the hydrogen content of this fuel is a directional predictor of soot. This is what the image at the bottom right is saying, is that there are things that don't help you predict at all the soot emissions from your fuel, so the physical characteristics of the fuel don't help you. But hydrogen content and the degree of hydrocarbon saturation are the highest correlated and most predictive measure you can get. There are some debates around how simplified this hydrogen content is and whether it needs dedicated limits. At the moment, only different specific species are addressed by the certification. So when you increase the hydrogen content of the fuel, you can get reduction in NVPM number by 20 to 80%, depending on the case. But again, engine technology can achieve very large reduction, especially lean burn engines that can run at very low soot emissions indeed. Things get more complicated when you look at volatile particle matter, because here the relationship with fuel composition depends on the non-volatile particulate matter level, so on soot, that's the soot-rich and soot-poor regimes that you may have seen. But what you can say across all soot regime is that having extremely low sulfur content in the fuel will reduce ice nucleation. What extremely low means is a little bit unclear, but it seems that this is likely below or even well below 10 ppm, which is essentially below what we can measure. So essentially, if you want to get rid of the effect of sulfur, you really need to be very, very low in sulfur concentration. There are projects, and we will hear about them in this afternoon, that look at the role of other precursors of ice nucleation, like oil droplets, nitric acid, or organic compounds. So what happens if you remove the soot, and then if you remove the sulfur, what else will form the contrail? But those remain open questions. So once you have reduced the emissions of particulate matter, you're expected to reduce contrail formation and therefore decrease the climate impact of contrail. But here again, the question is not so much reducing soot, but it's really reducing any source of particle because of suppressing soot will open new nucleation pathways. And something to remember, and that's the last bullet here, is that a reduction in particulate matter emissions will modify contrail forcing, but you will also touch other non-CO2 effects, and especially interactions between particles and radiation and particles and cloud, which in the case of sulfur are very likely to be cooling. So there is a question if that cooling turns out to be substantial. In the Lee et al. Assessment, it was not possible to put a bar on those effects. Well, maybe if that cooling is substantial, well, maybe we would like to keep it, and maybe it's a good idea to emit a bit of sulfur in the end. So having an idea of the net impacts will be important. So that's the 3 notes that are online now. Those are the notes that are upcoming this year in 2026. There will be one on NOx, which will be led by Volker Greve and Didier Blickstein. So why NOx? Well, if you the tools that are used to calculate the climate impact of flights in the EU MRV framework tend to give quite a large weight on NOx. If you run those tools, you will find that many of your flights will have a NOx climate impact that is larger in some cases than contrails and larger than CO2. And there are questions of why that is, that this tool, for example, are perhaps in disagreement with the assessment of IATA. So it will be interesting to see, to get some consensus on this. The second one is on navigational actions and Contrail Management. It will be led by Andreas Petikat of NATS and Mark Stettler of Imperial. So, well, it says, as it says on the box, it will look at what we can do around the control avoidance idea and what this means in terms of operations. So it will be interesting to see what kind of consensus we get within Hansen on the subject. And the third upcoming note is on the hierarchy of climate models, and here the idea is to give a little bit of clarity of what different models can and cannot do in the chain going from emissions to control formation to natural cloud response all the way to surface temperature change. That's all for me. You will find all the documents that I just referred to on the Hansen website, and we will also have more information about terms of reference and the list of members. Thank you.
So we do have time for a couple questions, and there's one online that I think we can take about climate efficacy.
Yeah.
You could maybe explain a bit why there's uncertainty about the
Yeah, so climate efficacy, essentially, that's a measure of how good relative forcing is at warming surface temperatures. And that's compared to CO2, which is taken as a reference. And the reason why contrails are perhaps not very good at warming surface temperature compared to CO2 is there's two things. The first is to form a contrail, you take humidity out of the atmosphere, and you essentially convert it into ice crystal. You can see an aircraft as a machine to convert water vapor into ice crystal in that way. And of course, now that you've formed the ice crystal with sediment, and you're essentially removing the humidity from the cruise level. And that means that the humidity will not be available for forming natural clouds later. So you can say that a part of my forcing, in fact, is just a change in timing of cloud formation. So I'm not exactly forcing the climate that way. And at the moment, the assessment is that it's reducing the forcing by between 40 to 60%. And then there is another question is once you have forced the system and you have added heat into the system, how does that heat goes down to the surface to warm the temperature? And here it's still unclear because it only comes from one climate model, but it's possible that because the heat is added aloft, it's and above the convective systems, it's not very efficiently brought to the surface, which will add another inefficiency. And here it could mean that we can get efficacies between 20 to 40% compared to CO2. So that's the questions that are currently open.
Great. Is there one more question from the audience? Stuart?
You did put it on slide, but I don't know if it came through.
Yes, but you want to ask it since you're here?
Shall I wait for the microphone?
Rose is running.
Just come to you. Sorry to hog the microphone. This is a deliberately stupid question. So, from a non-atmospheric scientist,
Is it possible that persistent cirrus could be created purely by the aerodynamic interaction of the aircraft with the atmosphere? In other words, even if there were no particulates in the fuel, for example 100% SAF or even hydrogen, is it possible that persistent cirrus might still form?
We can form contrails purely for aerodynamical reasons, although it's rare. It happens, I think, as far as I know, most often with military aircraft. But persistent contrail, probably not, because you would need to have enough ice crystals which are large enough to persist, and I don't think aerodynamic contrails are in that category.
Thank you.
But you could form an ambient aerosol, maybe.
You can form an ambient aerosol, but yeah, it depends on the ambient aerosol concentration. The best one to form a contrail on would be mineral dust, but obviously ingesting mineral dust into an aircraft engine is probably not a good idea.
Okay, we'll continue this session on Contrail research priorities and roadmaps, moving to the UK with Mark Stetler, who is going to talk about highlights from the UK Jet Zero Non-CO2 Task Force report.
Okay, good afternoon. I ran a half marathon yesterday, and I'm quite happy with how it went because I can still bend my knees. I've been able to cycle here this morning. But one of the reasons why I did that was because I'm running a full marathon in May for the first time. I think it's some early midlife crisis that's come upon me. But if there's one thing you remember from this talk, which has nothing to do with contrails, is that you don't just turn up to run a marathon, right? You have to practice, and you have to go and train, and you have to maybe run half a marathon to get used to running long distances. There is a contrails connection there, because if you want to implement contrail mitigation at scale, you have to develop the capability to do that. What I'm going to do with this talk is briefly tell you where we are in the UK in terms of the strategy coming from the Department for Transport, and then talk to you about two reports that I was recently involved in, one looking at recommendations for large-scale contrail avoidance trials in the UK, and the second one, which was around how do we think about the capability and what's the right framework for thinking about capability for contrail avoidance in the UK, and what elements do you need in order to do that? Okay, so taking us back to the previous government, July 2022, we had the Jet Zero strategy. And on non-CO2, this committed to developing understanding of non-CO2 impacts and potential mitigation, developing and implementing policies to address and reduce non-CO2 impacts, working with industry, academia, including the Climate Change Committee, to explore means of estimating and tracking non-CO2 emissions from the UK aviation industry. So the trajectory was set in 2022, and we have been making progress on that. So the Jet Zero Council, as it was previously called, closed in November 2024. Before they closed and before the end of the last government, they commissioned 4 reports, 4 action groups on non-CO2. The first one on recommendations for a UK-led contrail avoidance demonstration, which I will talk about. And then action groups on humidity sensing, a UK-led MRV system, and then finally the nature and scale of uncertainties linked to non-CO2 emissions. Since the new Labour government took over, there's a renaming of this council, so it's now the Jet Zero Task Force. And they set out their objectives. One of them included working together to better understand and address aviation's non-CO2 impacts. And that's in the minutes, the public minutes from December 2024. And that led to the formation of a Contrail Impact Mitigation Task and Finish Group. and that has recently reported, that's the second report I'll talk to you about, that has recently reported into this Jet Zero task force, saying that there should be a body responsible for testing contrail mitigation measures, and the UK should run a properly designed trial with the opportunity for the UK to show global leadership on this issue. So that was just a couple of months ago in January 2026. So if you're kind of familiar with political colours, the Conservative Party on the left and then the Labour Party on the right, they're the opposite colours in the US, just for clarity. Okay, so we also, in the meantime, have had things like the non-CO2 technologies roadmap from the Aerospace Technology Institute. They have a non-CO2 program of funding. We have had several calls from the Natural Environment Research Council, and Neil Harris, who is now the coordinator for this program, will talk after me. There you are, Neil. And also in January, we had a press release from the government saying there's a £43 million boost for green aviation, which can also be used for trials to understand how contrails could be avoided. Right, so I'm relatively optimistic about where we are in the UK in terms of having different parts of the puzzle in place and government support for this. So what did we say about recommendations for a UK-led contrail avoidance demonstration? I don't have a huge amount of time to go into all of the technical detail, and I would say that this isn't a set of recommendations for how you would run a trial, the how. It's more a set of recommendations as to why and who you would get involved and what that should look like, what the key features would be. So start with this picture here. What we're seeing here is some detections of contrails. Actually, this is obviously the Americas. We're using the GOES satellite here. And on the right-hand side, you can see that the NAT tracks, which are used to direct some of the traffic over the North Atlantic, we can see that those waypoints are visible in these contrail detections. Okay, so the fact that we're having aircraft form these lines across the North Atlantic. So clearly, it would be great if we could demonstrate that it was possible at scale to reduce these contrails and be able to observe that, be able to observe the radiative effects as well. And as has already been mentioned, there's been a range of trials that have been run. They have mostly been airline-led trials, and two of the things that often get mentioned about airline-led trials is that, one, if one airline does something, then another airline's just going to take up that space in the sky, and so you're not really achieving something that has a net benefit. And secondly, it's actually quite difficult to attribute individual contrails that are formed to specific flights, particularly in these regions. And this graph sort of shows it, because the fact that we can see these contrails kind of merging on top of each other, forming these almost lines in the sky, suggests that it would be very difficult to attribute one contrail to one flight. This image also shows us, so we're taking the GOES images on the left-hand side, the geostationary satellite, contrail detections in the middle, and then accumulated detections on the right-hand side. What you can also see from this is that it takes some time. So this is 1 day of activity in 2025. It takes some time to build up this picture of where contrails are forming and the effect that they're having. So it takes some time between contrail formation and the ability to detect that. And so it's not as simple as saying, well, we're going to turn off contrails for an hour and turn them back on and then be able to measure something. You need to think very carefully about how you set up a demonstration, a trial, and a control. So what you're measuring against. So here's all of the names on the action group 1. Too many to read. But the summary was that contrails are a significant part of aviation's climate impact. Aviation is a complex system where safety is a priority, so there's multiple layers and multiple elements of the system. And we need further advancements in science and technology to support contrail avoidance, which includes weather forecasting and contrail observations. The question we were trying to answer was, how can we demonstrably cut aviation contrail impacts for those thousands of flights that operate in UK-controlled airspaces, including the North Atlantic? And so we proposed UK UK-led contrail avoidance trial that achieves operational implementation and quantification of the reduction in contrails resulting from those contrail avoidance measures. So we've heard it already. You know, these ISSRs are what we want to avoid. You could try and fly around them. You could fly above or below them. That's the kind of concept that we're working with. And the features of the trial that we're proposing is that you need three key areas. One, which is scientific rigor. So you need to have an appropriate control. That's both in terms of contrail impacts, but also in terms of any additional fuel burn that might result from this. And to the point that was raised earlier on, if you have lots and lots of flights, so you need large-scale data collection, you can use statistics to improve your confidence in the effect of the intervention that you're taking. Second aspect is operational practicality. So we predominantly looked at quieter airspaces, and we're looking at an ANSP-led trial. That's what we're recommending in order to be able to do this at scale. And then the third feature would be scalability. So looking at real-world airspaces under a variety of meteorological and air traffic conditions, although focusing on those quieter times of the day. So bearing in mind, this report was this sort of positioning ourselves, motivating motivating us to do this. So I'm just going to kind of inject some competitiveness into this. This quote came from the US National Academies of Sciences. It says, "The United States is strongly positioned to conduct contrails research to enable the country to have a competitive advantage, both economically and diplomatically." Well, I think we're better placed here. I think we have large airspace in the North Atlantic that's controlled by NATS. We have the Met Office, which is one of the two ICAO World Area Forecast Centres. We have a very important aerospace sector in the UK. We have, I'll say it myself, world-leading academic research, government support, and R&D funding, including from the Aerospace Technology Institute. So to put some numbers on the North Atlantic, it's about 1,400 flights per day, or 500,000 flights per year, about 19 million tons of fuel per year, about 60 million tons of CO2 per year, and depending on, using a 100-year time horizon and a global warming potential and an efficacy factor of 0.42, it's about 35 million tons of CO2 equivalent from contrails per year. So there's a huge opportunity. And there's an opportunity for the UK to lead this at a global level. I'm running out of time, so I'm going to go a little bit quickly. The Climate Change Committee have actually looked at non-CO2, and it's part of what the Climate Change Committee, so they're the independent statutory body established under the Climate Change Act to advise the government on climate and climate mitigation. While contrails they are out of scope of the net zero targets, the Climate Change Committee forecasts that warming from non-CO2 effects are expected to increase in 2040 and 2050 relative to 2025. And they say actions to reduce both CO2 and non-CO2 effects are therefore equally important, and that they recommend the UK commits at a minimum to preventing the additional warming impacts from aviation beyond greenhouse gas emissions increasing after 2050, and that we need to begin to monitor these and support investigation, development, and trial of mitigation options that complement rather than substitute CO2 mitigation. So, there's a lot of momentum now behind this. In the report, we looked at these two, Shanwick airspace and Scottish airspace. They are different. These two are both controlled by NATS. They're different in the way that flights are monitored, but also the pattern of air traffic. So Shanwick in the North Atlantic, predominantly cruise traffic at deconflicted levels. That means aircraft flying in different directions or at different flight levels. Whereas the Scottish FIR is radar controlled, but it includes a more complex mix of different air traffic. We are not saying how to do this exactly. I think that's an exercise that needs to happen after there is support for a trial. including looking at exactly when those periods are where you would do a trial, what instructions would be provided to airlines or what that communication is, and also how you would specify a control period, so those periods where you're not taking any action. Two kind of technology enablers. We need better forecasts, so that includes weather forecast models. It could also use observations, and there's a piece around how do you implement that data, both by ANSPs and airlines, including timelines. So when is that forecast provided? How does that get incorporated into flight planning or tactical avoidance? And the resolution of that data and what the data is. And secondly, we need developments in measuring the effectiveness of contrail avoidance. So we're predominantly we would have to rely on geostationary satellites, so Meteosat third generation. The image on the bottom right here shows some contrails detected in that Meteosat third generation. The detection and attribution is difficult. The radiative effect is difficult, especially over very small numbers of flights, but that needs to be developed. And as I've said already, the counterfactual is something that needs to be thought through carefully. We had 9 recommendations, so I could read them all and take up a lot of time, but I won't do that. I'll kind of say that we concluded to say that airspace scale trials are necessary, that large-scale demonstrations should be supported by UK government funding. NATs are a critical enabler of any UK-led demonstration. Fourthly, safety cannot be compromised, and these ones are about engagement, about having independent oversight. So, that there needs to be some transparency. There needs to be transparency and review of the information that's the effectiveness of this trial. That the Met Office has a role to play and should be tasked to improve weather forecasts for contrail-forming regions, and that the effectiveness of contrail avoidance should be measured. Right, that's really important. So it's measured as far as we can, and including trying to measure that radiative effect. Okay, so I'm running out of time. So this second report is the Contrail Impact Mitigation Task and Finish Group, which was reporting into the Jet Zero Task Force. Here are all the names. Again, a mix of industry, from ANSPs to airlines to OEMs, a wide range of people involved in this exercise. And the thing that we were encouraged to do by Airbus was to think systematically about this problem. So how do we can think in a way that structures our assessment of the capability today and what is required in order to advance the capability? So this requires, we lent on the capability maturity model. So at level 1, you really know nothing. And at level 5, you know as much as you can about the system, and you're optimizing your processes in order to deal with the problems at hand. Right? And in between, there's different steps and levels of maturity. And then you might say, well, okay, there's different parts of our system. There's an element 1, for example, that might be airline operations, or there's an element 2, that might be weather forecast capability, etc. And you can kind of assess how mature those different parts are. And the idea is that in order to achieve at scale operational contrail mitigation, you would need to have high levels of maturity across these different elements. The key findings from this were that the UK capability remains at level 2, that's reactive. Despite the world-class research, no workstream has yet achieved standardized status. So everything is reactive at the moment. There are some blockers, and there's a strategic gap, which is the current trials are too small. So large-scale trials are needed in the North Atlantic corridor, which is managed by the UK, and also this generates a disproportionate contrail warming impact. And there's also this systemic interdependency. So airlines are constrained without OEM tools. Regulation needs to be underpinned by science. and a roadmap for implementation is essential, rather than a fragmented approach which will cause further delays. So the key recommendations that came out of this was to establish a governance body to implement large-scale UK trials, adopt this maturity level framework, and that would also help develop and enable policy, so develop the necessary regulatory framework and operational procedures to transition mitigation from trials to business as usual. This is the table. All of these elements were aircraft and engine OEMs, airline operations, climate impact, weather data, ANSP operations, fuel production standards, regulation. They were mostly at level 2, some of them at level 1, and we looked at what would be required in order to get to levels 3, 4, and 5. Large-scale trials support all streams achieving level 3. Okay, so you run half marathon in order to get to the marathon. And one of the key recommendations here is that a governance body is needed to coordinate level 3 to level 5 activities. So going beyond a fragmented approach and really having a governance body to try and move all of these different elements together at the same time. So I'm out of time. Apologies, Nellie. These are my conclusions, which are my own rather than of those groups. But large-scale trials are necessary to support the development of contrail impact mitigation and maturation of the required elements of the system. Mitigation of aviation's non-CO2 emissions are required by the Climate Change Committee, so this is not just an aviation issue. And thirdly, we have all the pieces required to run a large-scale trial in the UK, including industry, academia, and government support, importantly, in order to do that. So thank you for listening.
Okay, we're going to hold questions until after and continue with the UK. Neil Harris is going to give an overview of all this government support, the projects that they're funding.
Okay, good afternoon, and many thanks to the organisers for inviting me to give a talk on this programme. I'd like to thank Mark for giving the overview of the UK situation, which I thought was excellent and better than I could have done, so that was lucky. And I wondered if we could have a sweepstake on how far he's running by the time we all reach level 5. So I think it might be quite a long distance by then. So I'm talking today about the ATI-NERC part of what he said, which are the research projects leading up to hopefully quantifying some of the results that help the other sections. And I'm the newish coordinator for this program, and so getting on top of that one. Yeah. There we go. Oh, sorry, there we go. Sorry, because there's at least one of the funders in the room. So I should point out that this is well funded across government. It involves the Department for Transport, the Department for Trade, and Innovate UK, with Aerospace Technology Institute and NERC are the two institutes who are running the projects themselves. And so the coordination runs across the Aerospace Technology Institute project and the NERC, the Natural Environment Research Council ones. And that was deliberate in the design of the program in order to start integrating across the two parts of the basic research on the atmosphere, which we heard a little bit about earlier, but also the technology and operations side, which is needed to reach the level 5 we just saw. And so the program is really spanning these two parts of the program. And the aim is to be really thinking, how can we integrate them to the most effect? And that's different from what the individual projects are trying to do themselves. It has a major bias, if you like, or emphasis on Contrail measures for the next 5+ years. But it's also aimed to cover the NOx, for example, and to inform other investment decisions for the longer term zero carbon options, including SAF and hydrogen in particular. So the opportunity is to be trying to reduce the impacts of the climate impacts of the non-CO2 emissions. To do that requires increasing certainty in what they actually are, either at a global level, the top-down referred to earlier, or individually from the bottom up. And in principle, contrail reduction could start in the next 5 to 10 years if we can reach that level 5. NOx and contrail reduction are required also for SAF, which SAF may or may not come on stream in the next 5 to 10 years in significant amounts. So it's avoidance for the kerosene at the moment. Early decisions on NOx and limitations on hydrogen emissions are required in order to make early decisions for investments about what the technologies being invested in to pursue. And obviously, we want to be able to try to provide the best science we can as quickly and efficiently as possible. So the program is a £30 million program, which is quite big by UK standards. As I said, it involves NERC to the tune of £10 million and ATI to the tune of £20 million, and it's bringing together climate scientists, aerospace, and aviation experts in the different projects. Quite a few of the projects already involve those within the projects themselves, which is very reassuring. The academic-led research through NERC, if you like, is 10 projects were funded in round 1 and 6 in round 2. Those are being announced at the moment, so I can't say them here. And round 3 will be launching the call very, very soon. For the ATI ones, 3 are announced. 1 is coming very soon, and there are more in the pipeline, either which are being considered for the review panels, or which are coming in future calls through this year. The coordination team at Cranfield is myself. I'm an atmospheric scientist. Anna Smallwood, who's a professor of aviation and has an operational experience. Mark Westwood, who's the professor of aeronautics and has clearly an aeronautics experience. And Xinwei Kui, who's a research fellow in sustainable aviation, who's helping a great deal with this and brings knowledge of the SAF market to it. So we've got a wide variety of skills at Cranfield to bring to this problem. The most important thing in my mind that we'll do is to, first of all, to provide the cross-project connects, and that's starting to work already, and identify gaps and synergies between the projects, which is important for future calls. Equally, I think we will be coming up with program-wide initiatives which are more top-down in the sense we'll answer broad questions that can be addressed by several of the projects across the program. And for that, we'll be looking for input from a wide variety of people, many of whom are in the room, so do lobby me if you want, on what those broader questions should be. And I imagine that Mark, anyway, would have ideas on that, having got the content of that overview presented already. They'll be first discussed at the program annual meeting, which will be in Cranfield on the 20th and 21st of May. And that's when we'll start and probably define the first 1 or 2 of the initiatives that we'll do over the next 3 years, without at least developing good ideas for the others. So coming up with some fairly crude areas of research topic to try and give you an idea of what they are. 3 are related to contrails, 3 of these areas, and you can see if you look at the numbers on the right that that's the bulk of the projects. There are 5 sort of 5 through NERC and 1 through ATI, which are focusing on uncertainty reduction for impact and operations in the ongoing projects. And that's sort of a near-term thing which will directly help any Contrail trials. Then there are another 7 through NERC. This includes the 2 rounds, in case you're wondering why it adds up to more than 10. It adds up to 16 because of the 2 rounds. Looking at alternative fuels, and 2 within the ATI remit are looking at that and their impact on alternative fuels. And one of which will be discussed later, the Kritos project is related to that and their efficient air availability. And then the contrails through future aircraft technology, which is related to the aircraft design question at the back. And it's not my area, so you're not allowed to ask me the question either. So there are 2 on NOx and 1 on the metrics, which always come about. What I'd like to say at this point is there are 2 projects which rely on chase measurements, where a research aircraft flies close behind an aircraft with a known engine and a known fuel, etc., etc. They're about halfway through their flight hours at the moment, and unfortunately the National Environment Research Council has cancelled the FAM aircraft with immediate effect. We're currently assessing what the impact of those is, and Paul may talk about it a bit more for his project when he talks, or he may not, I don't know. But we're assessing that. But my worry is it'll be a major loss going forwards. We won't be able to do this type of research in future. And the DLR plane that Christiana will talk about is busy enough anyway, so I'm worried that we're lacking capacity in this. I raise this because personally I think it is an issue for the whole room, and if anyone wants to follow up on me, we can do so after this, during this meeting. So I'll now look at 5 individual projects in summary to give an idea. So this is from the funded ones, an idea of the scope of the projects that have been funded. There's one called Magica, and its title gives the game away. Modelling Aviation, Global Climate Impacts from Contrails, Climate Impacts from Contrails and Aerosols. And this is using 2 state-of-the-art climate models, so it's not simple models as Olivier Boucher described earlier. These are the full-up climate models, looking at the processes to understand the interactions between contrail cirrus, aviation cirrus, and the clouds in the atmosphere themselves. So this is a very complex problem, and it is for climate generally, let alone when we just look at the aviation component of it. So they're making progress so far, and papers are starting to come out on this. The next one is on contrails from SAF and hydrogen combustion, and it involves both models, which you can see in the colourful pictures in this slide, and also developing a new measurement facility at Imperial College. The point of this is to really be able to look at things like the ice crystal number and the water vapor saturation in the plumes or the near field plumes in some detail here. So that's important to understand the mixing of the plume itself into the ambient atmosphere. And so these LES models, large eddy simulation models, are very high, got a blank on order, very high quality and high definition work to look at this, and they've been coupled with aerosols and with ice microphysics. That's brought it up. That now has been added to with the volatile particle activation, which means it can look in the early stages at the what happens within the contrail in its early stages. That has been compared to work from NASA a few years ago, and it can now start to be compared with the new facility in the UK. And he's sitting next to me, so I will be marked on that when I sit down. Thanks, George. Mark mentioned the importance of observing individual contrails. There is work going on here to try and improve the capability of doing this, led by Ed Griesbeet at Imperial. And this is a multi-instrument approach to the problem, involving cameras, radar, satellites, and satellites for a couple of reasons, one of which is to look at the contrails, the other which is to look at changes in natural cirrus. I won't go through the bottom half of the slide, but it's trying to come up with this integrated solution to be able to track contrails and their impact on the atmosphere through the cirrus. That's linked to one of the ATI projects, which I'm not describing here, where they're working on the improving the water vapor measurements from in the air traffic lanes by actual measurements. And so basically that's being led, I think is the Airbus one, is being led by Airbus, and so that's trying to develop that side of it. And between the efforts going on here or in other countries, I think we will be ending up with a much better observation system in the next few years. So I'll be optimistic on that. Whether more's needed to pull them together, I'm not quite sure. The SAFICE project is one which is run by Ben Murray at the University of Leeds and involves the APU facility at Sheffield. So it is an aircraft engine, and it does not have a contrail producer around the back of it. You just measure in the hot plume. So what they've been doing is looking at both the plume, but also the sampling of the lubrication oil alone. And by doing it in a rig in a lab, you can try and pull out the lubrication oil part of the problem. And what they find is that both the lubrication oil and the core plume affect the number of contrail particles. So just reducing the number of contrail particles in the core plume will not reduce those in the contrails overall, is the finding to date. They're doing more experiments in Sheffield starting next week, I think, and so there will be more fleshing out of these results as we go down. But hot exhaust core venting likely produces the stronger contrails as things stand at the moment. But we should know more really quite soon on that. Finally, I'll do one from the ATI program. And this is a startup company. The other two are led, I mentioned one by Airbus, and there's one led by BA that we'll hear about later in the meeting. And this is about trying to produce SAF in a different way. Basically, they're experts in catalytic conversions, so they're trying to do it in a very efficient way. And in terms of the SAF, they will be able to produce it with different levels of aromatics. Those aromatics will then be tested at the same facility in Sheffield to see what the impact on the engine output are. And obviously the idea is that the aromatics are a key part of what's generating soot and particulate matter from the plumes. And I think that was it. So that was just a slide I showed earlier, so I didn't end up with a thank you slide. So, thank you.
We have time for one question for Neil and one question for Mark Stetler that have come up in the Slido. So for Neil first, so this was about what are the implications of our progress in contrail research given the course of the UK's aircraft facility FAM? I'm not aware of another aircraft facility that stands a chance of getting the requisite altitudes, let alone measuring contrail properties. Have you addressed that already?
I addressed some of that, didn't I? Yeah.
Could you repeat the question, please? We didn't hear it.
Yeah. The question was, what do I think the implications are of the lack of the FAM aircraft in future for air traffic research? I think it was put on that. there are immediate implications for two projects in the program I just mentioned, and we're sort of trying to get to the bottom of those as to what alternatives there are for that. Looking down the road, we would lose any capability to chase experiments in future. My personal view is that as we develop more different types of SAF, they will only become more important to do, because unlike things like NOx or CO2, which a lot of ground testing is done for the ground level emissions, if you like, I think that'll be much less meaningful for the contrail emissions going forward. I think that part of it just needs that. In Europe, that would leave the DLR aircraft, as I said, particularly the Falcon, I think, unless that's changed since I last looked. But that's already very busy, so you can't add much to the load there, is my understanding of that. In the US, I think we have a US speaker coming up, and my American wife told me I shouldn't comment on what might happen in America at the moment. But they have that facility at the moment. If that can be maintained, then there will be 2 aircraft left. And I think that, personally, I think it's a real shame for that and other scientific reasons. I mean, atmospheric scientists. But that's where I stand on it. So.
Mark, okay. Yeah, for Mark. Yeah. So regarding contrail attribution from Mark's presentation, could aircraft be equipped with rear view cameras and AI detection to transmit contrail data via meteorological data links? And what would the costs be?
So yeah, aircraft already do have cameras, so there's some potential to be able to use the cameras already fitted to aircraft, but they're not capturing and downloading that information. I'm getting a shake of a head, so perhaps that's of limited use. There is a project called Met that will be happening. Can I speak about it? And that will look at some of these data transfer issues. So if you have sensors on an aircraft, how do you get that data down from the aircraft and then share that data amongst others who might find that information useful? The cost, I have no idea.
Thank you. Hundreds of thousands? A lot. Great, okay, so now we're going to move to Ralph Iovinelli from US FAA, who's going to talk about contrail research priorities and why the US might be better placed.
Thanks, Nellie. Read those questions here. Please use the mic. Hi, everybody. I'm the American. Yep. Ralph Iovinelli. I know I didn't put any bio information, but I'll just introduce myself so that you know who I am. I'm the Emissions Division Manager in FAA's Office of Environment and Energy. I also wear a second hat internationally in the ICAO realm under the Committee for Aviation Environmental Protection. I also co-lead the group with a UK nominee, Dr. Bethan Owen. But her and I work together as co-rapporteurs on the emissions technical group in ICAO. So we're known as Working Group 3 in social circles, but that's kind of the label that was given our group. And yeah, we've been doing a lot of work on emissions for decades. And so it's a pleasure to be here, and thank you to Nellie and IATA for inviting me here. I'm not going to come with a lot of technical information, but I think there was a lot of truths that were spoken today. As you can see, it takes a lot of resources to do this kind of research. It's not trivial. And so if we can go to like my first slide, I feel like there's a couple things that we probably need to talk about in advance, and that is what I'm going to show you is not only a historical review of of the type of campaigns that the FAA has thought highly of to be part of over the years, but I also want to give you a forward-looking sense of some of the projects that we have funded coming forward. So you can kind of see how we're working in this space at the moment. It's not a new space for us, but it's an important one. And certainly what we've learned, if anything, is that it takes more than one organization to do these things right. So partnering and collaboration is really important. Also, before we get started, I just want to shamelessly give a plug for an upcoming event. The FAA will be sponsoring a meeting at the end of June 29th and 30th in Washington, D.C., focused on contrails. So bring all the science and information to that. Hopefully we can all collaborate there. If you're familiar with the AEC roadmap meetings that we've been having for 20 years or so, it'll be very much like that format. And so hopefully we can see you guys engaged in that as well. So let's get started. I think probably if we go to the next slide, I'll just start off with some preliminary obvious things to point at. Do I move the slides, or how does this work? Do I move the slides here? Sorry, I guess I should look at the equipment I'm handed. Right. Thank you for advancing the slides, whoever did that. I'll take it from here. Appreciate it. So we have a web page. You can go visit it, and it talks about things that contrails do offer up in the sky. It talks about patterns and colors and shapes and things of that nature. So you can go there. There's also a fact sheet if you want to download that. But most importantly is our new contrail research initiatives I want to highlight here to kind of integrate with what's going on or been mentioned so far. Wow, this got stretched. Those were not ovals, but they're circles. But anyways, they're ovals. This is, yours truly developed this slide, so sorry about the eye chart. But I was asked a year ago, what contributes to our knowledge base on contrails? And this is part of the answer I gave. We've got 30-year trajectory of research in this area. It's not trivial. I think what you take from this slide is that what I've said before, you can't do it alone. You have to team. You have to collaborate. I think some of the hand-wringing in this room about assets like aircraft to chase an aircraft or to get the aircraft that can be chased, these are large assets that are not trivial. And if one goes down, you're left in a lurch, right? If more than one goes down, you're basically done. But this gives you a 30-year trajectory of kind of the type of major investments that the FAA has made. And you can see, you know, working with other groups, DLR, NASA, and others, this is not trivial. This is a lot to do. And it's just the beginning. This was just kind of teaching us about particles, teaching us about gases, teaching us how cloud physics works, things of that nature, very basic stuff. But it's this kind of investment that got us to where we are today as a group. You know, we walk amongst you guys, and it's this kind of knowledge base that is needed for this kind of challenge. Some things that we focus on these campaigns are on the bottom. We do strive for collaboration and data sharing. That's really important. We understand that you can't solve it, but you can lower the uncertainties, and that's a really important aspect to this topic. And of course, we look for a lot of robustness and consensus from the scientific community. That's a real driver, and it allows us to make good decisions in the future. So with that backing, you know, we're certainly not new to this area. We might not be super active, you know, across the pond. We don't feel the pressures like they are felt here, so we understand that. And it's usually those kind of pressures that spur a lot of innovation and excitement and good activity. And it just shows you the genius that Mark is, where he said, you know, there was a report that was released by our National Academies of Sciences that says the U.S. is well positioned to lead this. It's well positioned. We're not doing it, but Mark, I think that shows your genius that, you know, when you poke the bear, we get things done quicker and more efficient. Maybe it wasn't Pearl Harbor, poke the bear. But it was a kind poke the bear, and we appreciate that. No worries, Mark. It's all good. We'll hug it out later. All right. So anyways, let's move on. I'm really excited to just walk you through the next few slides just to show kind of our commitment in this space at the time. So right now, we're approved to move forward on some good measurements. These are the hard-to-do things, like Mr. Harris just explained. This is where you get an airplane at altitude and you chase it with another airplane. And there's phases to that. It's not just do it and you walk away, but there's also some ground truthing to it where you take measurements on the ground and you compare them and contrast them to the measurements made at altitude. These are things that are very important to bring forth the robustness of the science measurements. It's really important. And so you can see if some of these campaigns on the screen here speak to that. If I go back one slide, I'll just point to the last yellow oval on the far right of the screen. So in last year, 2024, we did do some work at Gulfstream to do some ground tests. We were able to successfully separate the lube oil emissions from the exhaust emissions. That's a really important thing to kind of decode this activity at altitude. So you can see that follow on to that, if I go to the next slide now, the first bullet under campaigns is to now do the chaser plane equivalent of that. We've done all the ground level measurements. Now we're going to go in situ and measure them and see how it plays out. So we're really excited about that first opportunity. That's next month. So we've got all of our resources focused on that, and we're really excited to get that going. Beyond that, we're also looking to do some ground measurements, as you could see, 3 ground measurements for a number of different aircraft, Airbus and Embraer, with various levels of Pratt engines, geared turbofan engines. So that's a really exciting thing that we hope to accomplish. We're funded to do it, and we're excited to see those campaigns go forward. Of course, this is working with a lot of other governments. Certainly in Maribel, we'll be working with Transport Canada and the Canadian government there, as well as Airbus and Pratt. Certainly the ground measurements later on for Embraer and the A320neo, those are certainly more European efforts, which we will be collaborating with DLR and other key partners in this space. So this is a really exciting thing. And of course, we look forward to making those successes as much as we can. Beyond that, we also understand the importance of the volatile particle contribution, and we want to unpackage this as best we can. It's one of those, influences that we really haven't paid a whole lot of attention to, but the volatile particle component cannot be overlooked. And so we're going to do a couple things here where we're going to do some model development, understanding the microphysics involved. You can read the blurb on the screen, but it really gets to that understanding, first in the lab, and then when we take those lessons learned from the lab to the actual measurement campaigns in situ, we really learn a lot. So we're going to start with Ascent. We call it 107. It's just a name. But it's really got some experts in the field to kind of untangle the volatile particle side of things. And so we're excited about getting some successes in that, or clarity on those parts of the puzzle. Along those same lines, we also see further partnership and successes. You could see A4Climate and Suffice, which was offered up earlier. I mean, we're partnering with those kind of teams. And this is looking at better instrumentation, because we're all limited by our instrumentation capabilities, and this gets more to the instrumentation that could be developed, hopefully, to answer some very strong science questions on the non-volatile side or the semi-volatile side. So the organic species that come from lube oil would be better characterized by developing this type of instrumentation. We think it's a worthy investment. It does answer a lot of questions that are unanswered right now, and hopefully gets us all on the same page when it comes to the influence of those semi-volatile organics that come out of lube oil. So that speaks to the design today, but You know, all these kinds of efforts also speak to the transformation of the industry. And that's why we're here. Contrail research and development and understanding really will change our industry in many ways. You've heard a lot of presentations so far about telling pilots where to fly to avoid contrail generation. Yes, that's great. That's an operational change. But on the hardware side, which would be kind of invisible to the public, the gas turbine engines of the next generation of those are going to be a lot different. They're understanding the influence of lube oil. They're understanding how to redesign that conforming type design that gets certified for airworthiness. It's going to be a much different animal if this is taken seriously. And we'll stand at the ready to see how that comes out, but these are engineering solutions that we look forward to. And it's this kind of scientific effort that we're all talking about in the room here that feeds into the innovation within industry. So, you know, keeping the big picture in mind and understanding what tomorrow brings, we're standing at the ready to understand the transformations that this topic will bring to our industry on many levels. And so with that, I'm going to conclude with some words that I gave a presentation about a year ago to the Anson group. And these are really important concepts that we take strongly in the United States, and we hope it's shared. So certainly the first one is the most important, collaboration. Yeah, you can't do this alone, no way. Lowering uncertainties is a big thing. I don't think you can get rid of uncertainties in aviation, but you can lower them to the point where you're confident. And I appreciate Olivier's Anson presentation. There are some uncertainties that we deal with on the emission side in aviation. Probably our largest uncertainty right now is in non-volatile particulate matter, plus or minus 20%. And just as an anecdotal data point, we were told by ICAO Cape that plus or minus 20% needs to be reduced before they take any more decisions on NVPM. That gives you a sense of kind of uncertainties and sure-footedness that this industry asks for. Common data sets are really important. Let's learn to share. Let's learn to share often and frequently. It's always amazing to me, you can give 10 scientists the same data set and you get 10 really good, insightful answers. None of them wrong, but you know, focusing on different things. So let's push for that. Let's make sure that our peer-reviewed scientific journals are full with this kind of information. It really helps to build scientific consensus in the long run, and that's what we're after. Best practices and common terminology goes a long way. We use a lot of acronyms in aviation. We use a lot of terminology, and that needs to be defined and used in a common way. Otherwise, you're only talking past each other. And of course, we believe that bringing it to global decision-making bodies like ICAO Cape makes good sense for everybody involved. But that's for other people to determine. But I feel like we've gotten some really good, we've achieved some amazing goals when we pump things into ICAO. So I think that's one way of reflecting on it. And these are the parting thoughts. This is my last slide. I didn't take all 20 minutes, but I thought for sure that these were important things to bring forth in this workshop. I hope you found that interesting, and I hope you see that we're not lying dormant in this space. This is a common space for us. We've been working it for a long time with you guys, and we hope to do so more in the future. Thank you.